Next theorem, let A be a square matrix and let K be a positive integer. If lambda is eigenvalue of A with a corresponding eigenvector x, then lambda raised to the power k is eigenvalue of A to the power of k with a corresponding eigenvector x. So this theorem says, if lambda is eigenvalue of A with a corresponding eigenvector x, then if I raise A to the power of k, then lambda to the power k is eigenvalue of this matrix A to the power of k with a corresponding eigenvector x. Now let's prove it. Since lambda is eigenvalue of A with a corresponding eigenvector x, since lambda is the eigenvalue of A with a corresponding eigenvector x, then that means AX equal to lambda x. That means A times x equal to lambda x. And I'll try to show that lambda to the power k is the eigenvalue of A to the power of k. Next, if I multiply both sides by A, what do we get? If I multiply both sides by matrix A, I have A times AX equal to A times lambda x. Then on the left side, A times AX can be written as A squared x. On the right side, lambda is a scalar. A and x, they are matrices, so I can put lambda to the front. Write it as lambda times AX. Now what's AX? AX is lambda x. So we get A squared x equal to lambda times lambda x, which means A squared times x equal to lambda squared times x. So that's a matrix, that's a scalar, which means lambda squared is the eigenvalue of A squared with a corresponding eigenvector x. And similarly, if I multiply both sides by A again, I get A times AS squared x equal to A times lambda squared x. Then on the left side, A times A squared is A cubed. I get A cubed x. On the right side, lambda squared is a scalar. A and x, they are matrices, so I can write a scalar in the front. I get lambda squared times AX. Then what's AX? AX is lambda x. So I get A cubed x equal to lambda squared times lambda x. Then on the right side here, lambda squared times lambda x is lambda cubed x. Which means lambda cube is the eigenvalue of A cube with a corresponding eigenvector x. That's a matrix, that's a scalar. Lambda cube is the eigenvalue of A cube with a corresponding eigenvector x. So similarly, by doing the same procedure, we can eventually reach A to the power k times x equal to lambda to the power k times x. Which means lambda to the power k is the eigenvalue of A to the power k with a corresponding eigenvector x. So lambda to the power k is the eigenvalue of A to the power of k with a corresponding eigenvector x. Let's complete the proof. Next theorem. Let A be an invertible matrix. If lambda is eigenvalue of A with a corresponding eigenvector x, then 1 over lambda is the eigenvalue of the inverse matrix of A with a corresponding eigenvector x. So this theorem says if lambda is the eigenvalue of A, then 1 over lambda is the eigenvalue of the inverse matrix of A with the same eigenvectors. Let's prove it. First of all, let lambda be the eigenvalue of A. With a corresponding eigenvector x. Since A is invertible, then determinant of A cannot be 0. Since A is invertible, then determinant of A cannot be 0. According to earlier theorem, we know that lambda is 0. Lambda equal to 0 is eigenvalue of A if and only if determinant of A is 0. So if determinant of A is 0, then lambda equal to 0 is no eigenvalue of A, which means lambda cannot be 0. Since lambda is the eigenvalue of A, then lambda cannot be 0, according to the earlier theorem. Since determinant of A is not 0, lambda cannot be 0. Next, since lambda is the eigenvalue of A, with a corresponding eigenvector x, then A times x equal to lambda x. A times x equal to lambda x. Next, if I multiply both sides by inverse of A, what do we get? Since A is invertible, I can multiply both sides by inverse of A. What do we get? On the left side, inverse of A cancels A, we get S by itself. On the right side, lambda is a scalar. Inverse of A is a matrix. S is a matrix. I can pull out lambda. I get lambda times inverse of A times x. Since lambda is not 0, I can divide both sides by lambda. Since lambda is not 0, I can divide both sides by lambda. I get 1 over lambda times x equal to inverse of A times x. So if I switch left side and right side, I have inverse of A times x equal to 1 over lambda times x. That's a matrix. Inverse of A is a matrix. Over lambda is a scalar. If a matrix times x equal to a scalar times x, that means this scalar is the eigenvalue of this matrix. Hence, 1 over lambda is the eigenvalue of inverse of A. With a corresponding eigenvector x. That complete the proof. So, if lambda is eigenvalue of A, then 1 over lambda is eigenvalue of an inverse matrix with the same eigenvectors. Next theorem. Let A be an invertible matrix and let K be a negative integer. If lambda is eigenvalue of A with a corresponding eigenvector x, then lambda to the power of K is the eigenvalue of the matrix A to the power of K with a corresponding eigenvector x. So this theorem says, if lambda is the eigenvalue of A, then when we raise A to a negative integer power, then lambda to the power of k is the eigenvalue of this matrix A to the power of k with the same eigenvector x. Next, let's prove it. First of all, since lambda is the eigenvalue of A with a corresponding eigenvector x, since lambda is the eigenvalue of A with a corresponding eigenvector x, then A times x equal to lambda x. Also, A is invertible. Since A is invertible, then according to earlier theorem, lambda cannot be 0. If A is invertible, lambda cannot be 0. And 1 over lambda is an eigenvalue of the matrix inverse of A. So, for the inverse matrix of A, 1 over lambda is its eigenvalue with the same eigenvector. Next, since k is negative, since k is a negative integer, then L equal to negative k is a positive integer. If k is negative, I let L equal to negative k, then L will be positive integer. Then, according to earlier theorem, if lambda is the eigenvalue of A, then I raise both sides to any positive integer power. Lambda to the power k is the eigenvalue of the matrix A to the power of k. If lambda is the eigenvalue of A, I can raise both sides to a positive integer power. That means lambda to the power of k is the eigenvalue of the matrix A to the power of k. Here k must be positive. So according to the earlier theorem, I can raise both sides to a positive integer power. So I have A inverse of A to the power of L times x equal to 1 over lambda to the power of L times x. According to the earlier theorem, I can raise both sides to a positive integer power. I get inverse of A raised to the power of L times x equal to 1 over lambda to the power of L times x, which means this number is the eigenvalue of this matrix. According to the earlier theorem, we have this. Hence, A to the power of negative L times x equal to lambda to the power of negative L times x. And we know that since L is negative k, that means negative L is k. Hence, A to the power of k times x equal to lambda to the power of k times x. Therefore, lambda to the power of k is the eigenvalue of A to the power of k. With a corresponding eigenvector x. Next, let's look at a special case. let A be an invertible matrix, and let lambda be an eigenvalue of A with a corresponding eigenvector x, then A to the power of 0 is always an identity matrix. Since A is invertible, then lambda cannot be 0. Since lambda cannot be 0, a non-zero number raised to the power of 0 is always 1. Also, we know that it's always true that I times x is the same as x. Identity matrix times x is always the same as x. And x can be written as 1 times x. So we have identity matrix times x is the same as 1 times x. And here, we know that A to the power of 0 is the same as identity matrix. And number 1 can be written as lambda to the power of 0, which means we have A to the power of 0 times x equal to lambda to the power of 0 times x. So this equation can be written as A to the power of 0 times x equal to lambda to the power of 0 times x. Based on this equation, we can say that lambda to the power of 0 is the eigenvalue of the matrix A to the power of 0 with a corresponding eigenvector x. So lambda to the power of k is the eigenvalue of the matrix A to the power of k with a corresponding eigenvector x when k equals to 0. And according to earlier theorem, we know that this statement is true when k is greater than 0. When k is greater, it's a positive integer. Lambda to the power of k is eigenvalue of A to the power of k with a corresponding eigenvector x. And this statement is also true when k is negative. When k is a negative integer, lambda to the power of k is eigenvalue of the matrix A to the power of k with a corresponding eigenvector x. Since this statement is true when k is positive, negative, and when k is 0, then this statement is true for all integer k. So this statement here is true for all integer k. Since this statement is true when k is a positive integer, negative integer, or 0, this statement is true for all integer k. So, as a conclusion, we have the following theorem. Let A be an invertible matrix. If lambda is eigenvalue of A with a corresponding eigenvector x, then for integer k, lambda to the power of k is the eigenvalue of the matrix A to the power of k with a corresponding eigenvector x. Next, let's create a different theorem. If lambda 1, lambda 2, lambda k, they are distinct eigenvalues of matrix A, and v1, v2, vk, they are corresponding eigenvectors of each eigenvalue, then v1, v2, vk, they are linearly independent. So this theorem says, for distinct eigenvalues, their corresponding eigenvectors are linearly independent. Let's prove it. For this theorem, we'll prove by contradiction. So we assume v1, v2, vk, they are linearly dependent. We try to prove that's impossible. Assume they are dependent. We try to prove that's impossible. Since a set with v1 itself is linearly independent, since the set of v1 itself is linearly independent, then we can keep adding vectors into the set. Keep adding vectors into the set. Let R be the largest integer. Such that v1, v2, up to vr are linearly independent. So keep adding the vector into the set in order v1, v2, v3, when the set becomes linearly dependent with start layer, let R be the largest integer such that v1, v2 up to vr, they are linearly independent. Once it becomes linearly dependent with start layer. So keep adding vectors into the set, v2, v3 in order, v2, v3, v4, v5. Once the set becomes linearly dependent, remove the last element, start layer. Let R be the largest integer such that v1, v2, vr, they are linearly independent. So procedure looks like this. Add v2 to the set. If they are linearly independent, keep adding the set, keep adding elements. If it's linearly independent, keep adding element. Now we're gonna add v4. If the set become linearly dependent, remove v4. So 3 would be the largest integer, such that v1, v2, v3 is linearly independent. Once the set becomes linearly dependent, start layer. Remove the last element, start layer. That's the largest integer, such that v1, v2, v3 is linearly independent. And here, this integer r, it must be strictly less than k. If r equal to k, that means v1, v2 up to vk, they are linearly independent. But we assume v1, v2, vk, they are linearly dependent. So r cannot be k. R must be strictly less than k. So here, r could be 1, 2, up to k minus 1. R cannot be k. And since r is the largest integer, such that v1, v2, vr, they are linearly independent, then if I add one more element to the set, it will be linearly dependent. If I add one more element to the set will be linearly dependent. For linearly dependent set, if we set C1 V1 plus C2 V2 if we set C1 V1 plus C2 V2 plus CR VR plus CR plus 1 times VR plus 1 equal to 0, there exist non-zero solutions for C1, C2, CR plus 1 because they are linearly dependent. Which means C1, C2, CR plus 1 cannot be all zeros. They cannot be all zeros. They cannot be all zeros. Let me call this equation star. Next, if I multiply equation star by A, by matrix A on both sides, multiply equation star by matrix A on the left side and right side. Multiply this equation by matrix A. Then we have A times C1 V1 plus C2 V2 plus CR VR plus CR plus 1 VR plus 1 equal to A times 0. If I multiply both sides by A, multiply left side by A, multiply right side by A, that's what we get here. Next, I can distribute A. Since those are matrices, they are all matrices, I can distribute A. So I get A times C1 V1 plus A times C2 V2 plus A times CR VR plus A times CR plus 1 VR plus 1. On the right side, A times 0 is 0. Here, C is a scalar. A and V1, A and V2, they are matrices. C is a scalar, I can pull out scalar. I get C1 times AV1 plus C2 times AV2 plus CR times AVR plus CR plus 1 times AV plus 1, AVR plus 1 equal to 0. And here we know that V1, V2, Vk, they are eigenvectors. They are eigenvectors of matrix A. And lambda 1, lambda 2, lambda k, they are corresponding eigenvalues. So A times V1 is in a sense lambda 1 times V1, since V1 is an eigenvector of matrix A, and lambda 1 is its corresponding eigenvalues. So AV2 can be written as lambda 2 times V2. And AVR can be written as lambda R times VR. AVR plus 1 can be written as lambda R plus 1 times VR plus 1 equal to 0. That's what we have so far. Next, I can write lambda in the front. It can be written as lambda C1, lambda 1 C1 V1 plus lambda 2 C2 V2. Let me put it on the other side. Write lambda in the front. We have lambda 1 C1 V1 plus lambda 2 C2 V2 plus lambda R CR VR plus lambda R plus 1 CR plus 1 VR plus 1 equal to 0. That's what we have so far. Next, multiply this equation star by lambda R plus 1 on both sides. Multiply this equation by lambda R plus 1 on both sides. Next, multiply equation star by lambda R plus 1 on both sides. I get lambda R plus 1 times this equal to lambda R plus 1 times 0. Lambda R plus 1 times C1 V1 plus C2 V2 plus CR VR plus CR plus 1 VR plus 1 equal to lambda R plus 1 times 0. Then on the left side, distribute lambda R plus 1. Distribute lambda R plus 1. I get lambda R plus 1 times C1 V1 plus lambda R plus 1 times C2 V2 plus lambda R plus 1 times CR VR plus lambda R plus 1 times CR plus 1 VR plus 1. On the right side, lambda R plus 1 times 0 is 0. Next, take the first equation, subtract by this new equation here. Take the first equation, subtract by this equation. What do we get? Take the first equation, subtract by this equation. We have C1 V1 looks exactly the same, so it can be written as lambda 1 minus lambda R plus 1 times C1 V1. Second term, C2 V2 looks exactly the same, so I have lambda 2 minus lambda R plus 1 times C2 V2. Keep going. In the rth term, we have CR VR. Then we have lambda R minus lambda R plus 1. Times CR VR. Continue, there's one more term here. There's one more term, last term. Last term, they look exactly the same. We have lambda r plus 1 minus lambda r plus 1 times cr plus 1 vr plus 1 equal to 0. And for the last term here, since lambda r plus 1 is the same as lambda r plus 1, they can cancel. So last term becomes 0. Last term becomes 0, they can cancel. Last term becomes 0. They can cancel. This is 0. They look exactly the same. When we subtract, they can cancel. Last term can cancel completely. So this equation equal to 0. On the right side, 0 minus 0 is 0. On the right side, 0 minus 0 is 0. So we have CR VR equal to 0. On the right side, 0 minus 0 is 0. Last term can cancel. Last term on the left side can cancel. On the right side, 0 minus 0 is 0. That's what we have here. And we know that the set V1, V2, VR, they are linearly independent. Since V1, V2, VR, they are linearly independent. And this is a linear combination of V1, V2, VR. This is a linear combination of V1, V2, VR. That means all its coefficients must be 0. Then lambda 1 minus lambda r plus 1 times C1 must be 0. Lambda 2 minus r times lambda r plus 1 times C2 must be 0. And continue. Lambda r minus lambda r plus 1 times CR must be 0. Since V1, V2, VR, they are linearly independent. All coefficients must be 0. If they equal to 0, if the sum is 0, then all their coefficients must be 0. So lambda 1 minus lambda r plus 1 times C1 must be 0. Lambda 2 minus lambda r plus 1 times C2 must be 0. And continue. Lambda r minus lambda r plus 1 times CR must be 0. Since lambda 1 is not the same as lambda r plus 1, then lambda 1 minus lambda r plus 1 cannot be 0. Since all eigenvalues are distinct, lambda 1 is not the same as lambda r plus 1. So lambda 1 minus lambda r plus 1 cannot be 0. If this number is not 0, then C1 must be 0. When two numbers multiply to be 0, that means at least one of the number must be 0. If the first number is not 0, then the second number must be 0. So C1 must be 0. Since lambda 1 minus lambda r plus 1 is not 0, then C1 must be 0. Similarly, C2 must be 0, C3 must be 0, and until CR must be 0. So similarly, C2 must be 0, C3 must be 0, and CR must be 0. So C1, C2 up to CR must be 0. Next, plug C1, C2, CR into equation star, into equation star. Plug C1, C2, CR into this equation star. We have 0 times V1 plus 0 times V2 plus 0 times VR plus CR plus 1 times VR plus 1 equal to 0. Then 0 times any vector is 0. They are all zeros. Then we have CR plus 1 times VR plus 1 equal to 0. Since VR plus 1 is an eigenvector, it cannot be 0. Since VR plus 1 is eigenvector, it cannot be 0. If VR plus 1 is not 0, then CR plus 1 must be 0. If VR plus 1 is not 0, then CR plus 1 must be 0. When we have a scalar times a vector, if the vector is not 0, the scalar must be 0. If a scalar times a vector is 0, when the scalar times a vector is not 0, it's 0. If the vector is not 0, the scalar must be 0. So CR plus 1 must be 0. Since VR plus 1 is not 0, then CR plus 1 must be 0. Since we have C1 equal to 0, C2 equal to 0, CR equal to 0, and CR plus 1 equal to 0, what does it mean? If C1 is 0, C2 is 0, CR is 0, and CR plus 1 is 0, then in this equation here, if C1 is 0, C2 is 0, CR is 0, CR plus 1 is 0, that means V1, V2, VR plus 1, they are linearly independent. Then V1, V2, VR plus 1 together is linearly independent. That's a contradiction, because we assume R is the largest integer such that V1, V2 up to VR, they are linearly independent. So V1, V2, VR, if I add one more element to the set, it must be linearly dependent. So that's a contradiction. That's a contradiction. It's a contradiction. Once we find contradiction, that means our assumption was wrong. That means our initial assumption was wrong. That means V1, V2 up to VR, they must be linearly independent. Once we find contradiction, that means our initial assumption must be wrong. That means V1, V2 up to Vk, they must be linearly independent. Therefore, V1, V2 up to Vk, they must be linearly independent. They are linearly independent. So that complete the proof of the theorem. That complete the proof of the theorem, which means the different eigenvectors from different eigenvalues must be linearly independent. Eigenvector from different eigenvalues must be linearly independent. Next, let's look at a more general theorem. If lambda 1, lambda 2, lambda k, they are distinct eigenvalues of matrix A, and S1, S2, Sk, they are corresponding sets of linearly independent eigenvectors of each eigenvalue, then the union of the set S1 union S2 union Sk are linearly independent. What does it mean, S1, S2, Sk? In the earlier example, in example 2, we have two eigenvalues, lambda equal to 2, lambda equal to 1. Let me call the first eigenvalue lambda 1. Let me call the first eigenvalue lambda 1. Second eigenvalue lambda 2. So in the earlier example, we have lambda 1 equal to 2, lambda 2 equal to 1. What does S means? S represent the corresponding set of linearly independent eigenvectors. So for lambda 1, there are two linearly independent eigenvectors, S1, S2, 1, 1, 0, 1, 0, 1. So contains two vector. Let's call v1. v1 equal to 1, 1, 0. v2 equal to 1, 0, 1. That's S1. That's a corresponding set. That's a corresponding set of lambda 1. That's a corresponding set of linear independent eigenvectors of lambda 1. Now, S2. When lambda equal to 1, there is one linear independent eigenvector. That's the third one. Let's call x3 here. That's the third one. That's x1, x2. That's the third one. Let's call this x3. So when lambda 2 equal to 1, there is one linearly independent eigenvector, 1, 0, 2. So in the set, V3 is 1, 2, 0. That's what S1, S2 means. S1, S2 represent the corresponding sets of linearly independent eigenvectors. So in this example, lambda 1 is 2. S1 is these two vectors, V1, V2. Lambda 2 is 1. S2 is this set, V3 equal to 1, 2, 0. In example 3, again, there are two eigenvalues. Then we call 0 to be lambda 1. Call this 2 to be lambda 2. From example 3, we have lambda 1 equal to 0, lambda 2 equal to 2. What's S1? S1 is the set of linear independent eigenvectors corresponding to lambda 1. So when lambda equal to 0, we have eigenvector, we have one linear independent eigenvector, 2, 1, 1. Let's call this vector V1. That's S1. How about S2? When lambda equal to 2, we have one linearly independent eigenvector. That's S2. This vector for one set is called S2. S2 is the set of linear independent eigenvector corresponding to lambda 2. Here, S2 is the set of the vectors 1, 1, 2. That's lambda 1, S1, lambda 2, S2. Lambda 1 is the corresponding set of linear independent eigenvectors of lambda 1. And S2 is the corresponding set of linear independent eigenvectors of lambda 2. That's what S1, S2, Sk means. They are the corresponding set of linear independent eigenvectors of each eigenvalues. Now let's prove it. The proof is very, very similar. We prove by contradiction. We prove this theorem by contradiction. So we assume the union of the sets S1 union S2 union Sk, they are linearly dependent. Assume S1 union S2 union Sk. This is a linearly dependent set. Assume this set is linearly dependent. Assume S1 union S2 union Sk. This is a linearly dependent set. Next, since S1 itself is linearly independent, because S1, S2, Sk, they are the corresponding sets of linearly independent eigenvectors. So S1, S2, Sk, they by itself, this set by itself must be linearly independent. Next, I try to union S1 with S2, S3, S4, and so on, one by one. I try to union S1 with S2, S3, S4, S5, one by one. Let R be the largest integer. let R be the largest integer such that S1 union S2 union SR is linearly independent. Let R be the largest integer such that S1 union S2 union SR is linearly independent. How is that works? So think of this. Suppose S1 has vectors V1, V2. S2 has vectors, for example, V3. S3 has vectors V4, V5, V6. S4 has vectors V7. Each set has different number of vectors. I first of all union S1 with S2. If they are linearly independent, we keep going. I union S1, S2, S3. If they are linearly independent, I keep union. S1, union S2, union S3, union S4. Now, if S1, S2, S3, S4 together, this set is linearly dependent. I remove S4, go back here. Then here, 3 is the largest integer, such that S1 union S2 union S3 is linearly independent. So here, let R be the largest integer, such that S1 union S2 union SR is linearly independent. Then this R must be strictly less than K. Then this R must be strictly less than K. So R could be 1, 2, 3, 4, 5, up to K minus 1. R cannot be K. R could be 1, 2, 3, up to K minus 1. R cannot be K. Because if R is K, we have S1 union S2 union SK. They cannot be linearly independent. They must be linearly dependent. So R cannot be K. R must be strictly less than K. So R could be 1, 2, 3, up to K minus 1. And also, since R is the largest integer, such that S1 union S2 union SR is linearly independent, that means if I add one more set here, if I union one more set here, this set will be linearly dependent. If I union one more set here, this set will be linearly dependent. So S1 union S2 union SK union SR. If I union one more set here, if I union SR plus 1, then this set will be linearly dependent, since R is the largest integer, such that S1 union S2 union SR is linearly independent. That means if I add one more set here, this set will be linearly dependent. Next, let S1 union S2 union SR be the set of V1, V2 up to Vp. In general, each set contains at least one vector. In general, each set contains at least one vector. So here, P must be greater than or equal to R. Then we know that S1 union S2 union SR is linearly independent. Then we can say that V1, V2 up to Vp are linearly independent. Next, let SR plus 1 be the set of Vp plus 1, Vp plus 2 up to Vp plus Q. Since SR plus 1 contains at least one vector, so Q must be greater or equal to 1. And then we know that V1, V2, up to Vp plus 1 until Vp plus Q, this is linearly dependent. If I add S1 to the set is linearly dependent. So from V1 to Vp plus Q, this is linearly dependent. Next, if we set C1 V1 plus C2 V2 plus CP Vp plus Cp plus 1 Vp plus 1 plus Cp plus Q Vp plus Q equal to 0. Then, since they are linearly dependent, the coefficient C1, C2, Cp up to Cp plus Q, they cannot be all zeros. Then the coefficient cannot be all zeros. Then C1, C2, Cp, Cp plus 1, C1, C2 up to Cp, Cp plus 1, up to Cp plus Q. They cannot be all zeros. Let me call this equation star. Next, in this equation, I multiply both sides by matrix A. Next, multiply equation star. Multiply equation star. Multiply both sides by matrix A. So I get A times C1 V1 plus C2 V2 plus Cp Vp plus Cp plus 1 Vp plus 1 plus Cp plus Q Vp plus Q equal to A times 0. I multiply both sides by matrix A. Then distribute A. Distribute A. This can be written as C1 times A V1 plus C2 times A V2 plus Cp times A Vp. Distribute A. Since C is a scalar, I can write C in the front. A and V, they are matrices. C is a scalar, I can put C to the front. Plus Cp plus 1 times A times Vp plus 1 plus the last term we have Cp plus Q times A times Vp plus Q. On the right side, A times 0 is 0. Next, since V1, V2 up to Vp plus Q, they are eigenvectors. Since these V's, they are eigenvectors. When I multiply, I get an eigenvalue times the vector. We don't know what eigenvalue is. So for vectors from V1 to Vp, let's assume the eigenvalues are alpha. For vectors from Vp plus 1 to Vp plus Q, we assume the eigenvalues are beta. So for vectors from V1 to Vp, we assume the eigenvalues are alpha. For vectors from Vp plus 1 to Vp plus Q, we assume the eigenvalues are beta. So we have alpha 1 V1 plus C2 times alpha 2 V2 plus Cp times alpha P Vp. Now, from P plus 1 to P plus Q, they all belong to S1. They all belong to SR plus 1. Since they belong to the same set, they all have the same eigenvalue. They all have the same eigenvalue. So the eigenvalue is the same from Vp plus 1 to Vp plus Q. This vector belong to the same set. So the eigenvalue must be the same. So we have Cp plus 1 times beta Vp plus 1 plus Cp plus Q times beta P plus Q equal to 0. Where in this set, each alpha equal to lambda 1, lambda 2, up to lambda r, where each alpha equal to lambda 1, lambda 2, up to lambda r, and beta equal to lambda r plus 1. Each alpha equal to lambda 1, lambda 2, up to lambda r, since they are eigenvalues of the set from S1, S2 to SR. So alpha equal to lambda 1, lambda 2, up to lambda r, and beta equal to lambda r plus 1. Beta equal to lambda r plus 1. Since these betas are the eigenvalues of the vector from Vp plus 1 to Vp plus Q, they are vectors in the set of SR plus 1. Hence, since these eigenvalues are distinct, alpha cannot be the same as beta. Each alpha cannot be the same as beta. Since alpha could be lambda 1, lambda 2, up to lambda r, but beta is lambda r plus 1, so each alpha cannot be the same as beta. Next, multiply equation star by beta. Multiply equation star by beta. If I multiply equation star by beta, what do we get? We have beta times C1 V1 plus C2 V2 up to CP VP. Next is CP plus 1, VP plus 1, until CP plus Q, VP plus Q equal to beta times 0. On the left side, it can be rewritten as beta C1 times V1 plus beta C2 times V2 plus beta CP times VP plus beta CP plus 1 times VP plus 1 plus beta CP plus Q times VP plus Q. On the right side, beta times 0 is 0. Next, take this equation, subtract by this equation. Take this equation, subtract by this equation. Hence, in the first term, C1 V1 looks exactly the same. The only difference is alpha beta. So we have alpha 1 minus beta times C1 V1. In the second term, C2 V2 looks exactly the same. The only difference is alpha and beta. This is beta. The only difference is alpha and beta. C2 V2 looks exactly the same. The only difference is alpha beta. So you get alpha 2 minus beta times C2 V2. continue until the p's turn. Cp, Vp looks exactly the same. The only difference is alpha p and beta. So we get alpha p minus beta. Times Cp Vp. Next term. Cp plus 1, beta Vp plus 1. They look exactly the same. These two terms look exactly the same, they get cancelled. All these terms until Cp plus Q, Vp plus Q. They look exactly the same. Every time here gets cancelled. They all get cancelled. What's left is right side. On the right side, 0 minus 0 is 0. Next, since we know that V1, V2, Vp, they are linearly independent. Since V1, V2, Vp, they are linearly independent. Since V1, V2, up to Vp, they are linearly independent. Then, if I set the linear combination of V1, V2, Vp equal to 0, all its coefficients must be 0. Then alpha 1 minus beta times C1 must be 0. Alpha 2 minus beta times C2 must be 0. And alpha p minus beta times Cp must be 0. Since V1, V2, Vp, they are linearly independent, and this is a linear combination of V1, V2, Vp. If I set this equal to 0, then all its coefficients must be 0. Since each alpha is not the same as beta, then alpha 1 cannot be the same as beta. Hence, alpha 1 minus beta cannot be 0. Now look here. If the product of two numbers is 0, that means at least one of the numbers must be 0. Since alpha 1 minus beta is not 0, that means C1 must be 0. So C1 must be 0. Since alpha 1 minus beta is not 0, that means C1 must be 0. Similarly, C2 must be 0, and until Cp must be 0. Similarly, C2 must be 0, C3 must be 0, and so on, until Cp must be 0. Next, plug C1 equals 0, C2 equals 0, and Cp equals 0 into equation star here. Then what do we get? We get 0 times V1, 0 times V2 until 0 times Vp. We get 0 times V1 plus 0 times V2 until 0 times Vp. Next term we have Cp plus 1 times Vp plus 1 plus Cp plus Q times Vp plus Q equal to 0. And we know that 0 times V1 is 0, 0 times V2 is 0. The first p terms are zeros. Hence we have Cp plus 1 times Vp plus 1 plus Cp plus Q times Vp plus Q equal to 0. But these vectors, Vp plus 1, VP plus 2, VP plus Q, they all come from the set SR plus 1. Here, SR plus 1 is a set of linear independent eigenvectors. So these vectors must be linear independent. These vectors, VP plus 1, VP plus 2, VP plus Q, they are linear independent. Since these vectors, VP plus 1, VP plus 2, up to VP plus Q, they all belong to SR plus 1, then they must be linearly independent. VP plus 1, VP plus 2, up to VP plus Q, they are linearly independent. If they are linearly independent, this is a linear combination of VP plus 1 until VP plus Q. If I set this linear combination equal to 0, then all coefficients must be 0. So from CP plus 1 to CP plus Q, these C's, they are all zeros. So CP plus 1 until CP plus Q, they are all zeros. They all equal to 0. Next, since C1 equals 0, C2 equals 0, until CP equals 0, and CP plus 1 is 0, until CP plus Q equals 0. If all C's are 0, then it's a contradiction because V1, V2 up to VP plus Q, they are linearly dependent. So C1, C2 up to CP plus Q, they cannot be all zeros. So it's a contradiction. Once we find contradiction, that means the initial assumption must be wrong. So S1 union S2 union Sk, they must be linearly independent. They cannot be linearly dependent. They must be linearly independent. Therefore, S1 union S2 union Sk must be linearly independent. Let's complete the proof of this theorem. So keep in mind, if lambda 1, lambda 2, lambda k, they are distinct eigenvalues, then their corresponding sets of linear independent eigenvectors S1, S2, Sk must also be, if I combine this set together, it must also be linearly independent. In the earlier example, we have lambda 1 equal to 2, lambda 2 equal to 1. That's the corresponding linear independent set of eigenvectors. According to this theorem, if I combine S1, S2 together, it must form a linear independent set. So S1 union S2 equal to these three vectors, V1, V2, V3. It must be linearly independent. These three vectors must be linearly independent. And in example 3 here, if I combine S1, S2 together, they are also linearly independent. S1 union S2 has V1, V2. This is also linearly independent. That's about this theorem. Next theorem. For any n by n square matrix A, it has at most n linearly independent eigenvectors. How can we prove this theorem? it's clear that if x is an eigenvector of A, with the corresponding eigenvalue lambda, if x is an eigenvector of A with the corresponding eigenvalue lambda, then x belongs to the solution space of a homogeneous system. Then S belongs to the solution space of a homogeneous system, lambda I minus A times S equal to 0. Here, since A is an n by n matrix, then lambda I minus A is also n by n. Since A is n by n matrix, lambda I minus A is also n by n matrix. And we know that X is a column vector. In order to match the size, S must be an n by 1 column vector. So X must be an n by 1 column vector, which means X has n components. Therefore, X belongs to Rn. So every solution of this homogeneous system belongs to Rn, which means every eigenvector belongs to Rn. Every eigenvector of A belongs to Rn. Then X belongs to Rn. That means every eigenvector of A belongs to Rn. So every eigenvector of A belongs to Rn. Next, let S be a set of eigenvectors. Let S be a set of n plus 1 eigenvectors. Of A. Let S be a set of n plus 1 eigenvectors of A. Since every eigenvector of A belongs to Rn, then S is a subset of Rn. Since dimension of Rn is n, then we know that any subset of Rn with more than n vectors must be linearly dependent. Then any subset of Rn with more than n vectors must be linearly dependent. Since S has n plus 1 eigenvectors, S must be linearly dependent. Hence S is linearly dependent. Since S has more than n vectors, S has n plus 1 vectors, S must be linearly dependent. Hence S is linearly dependent. Therefore, it means any n plus 1 eigenvectors of A are linearly dependent. Therefore, any n plus 1 eigenvectors of A are linearly dependent. Or in other words, A has at most n linearly independent eigenvectors. Since any n plus 1 eigenvectors of A are linearly dependent, that means A has at most n linearly independent eigenvectors. Next theorem, let A be a n by n square matrix. If A has n distinct eigenvalues, then A has exactly n linearly independent eigenvectors. In this theorem, in order to prove A has exactly n linearly independent eigenvectors, we try to prove A has at least n, and at most n, linearly independent eigenvectors. Let's first of all prove that A has at least n linearly independent eigenvectors. Since A has n distinct eigenvalues, let lambda 1, lambda 2, lambda n be n distinct eigenvalues of A. And then we know that for each eigenvalue, there exists at least one corresponding eigenvectors. For each eigenvalue, there exists at least one corresponding eigenvectors. Next, let v1, v2, vn be a corresponding eigenvector. Of each eigenvalue. Then according to earlier theorem, we know that if lambda 1, lambda 2, lambda k are distinct eigenvalues of A, and v1, v2, vk are corresponding eigenvectors of each eigenvalue, then these eigenvectors, v1, v2, vk, they are linearly independent. So according to earlier theorem, we know that v1, v2, vn, they are linearly independent. Since v1, v2, vn, they are n eigenvectors of A, and they are linearly independent, which means A has at least n linearly independent eigenvectors. Hence A has at least n linearly independent eigenvectors. And according to the previous theorem, we know that A always has at most n linearly independent eigenvectors. According to the previous theorem, A always has at most n linearly independent eigenvectors. Therefore, together, A has exactly n linearly independent eigenvectors, at least n and most n together means A has exactly n linear independent eigenvectors. Therefore, A has exactly n linear independent eigenvectors. That complete the proof. So, if A has n distinct eigenvalues, then A has exactly n linear independent eigenvectors. And in this theorem, if A has exactly n linear independent eigenvectors, that means for each eigenvalue, there exists exactly one linear independent corresponding eigenvector. For each eigenvalue, there exists exactly one linear independent eigenvectors. So, note, in the above theorem, each eigenvalue has exactly one linear independent corresponding eigenvector. So in the above example, each eigenvalue has exactly one linear independent corresponding eigenvector. Hello everyone, today we will study diagonalization. First of all, let me introduce similar matrices. Let A and B be n by n matrices. If there exists an invertible matrix P, such that B equal to inverse of P times A times P, then we say B is similar to A. If B equal to inverse of P times A times P, then we say B is similar to A. That's how we define similar matrices. Note, in general, if B is similar to A, then A is also similar to B. If B is similar to A, that means B equal to inverse of P times A times P. If I multiply both sides by matrix P, I have P times B equal to A times P. If I multiply both sides by P. Next, if I multiply both sides by inverse of P, I have P times B times inverse of P equal to A. So A can be written as P times B times inverse of P. Next, if I let Q be inverse of P, then P can be written as inverse of Q. So matrix A can be written as inverse of Q times B times Q. Since P is invertible, Q is also invertible. So A is similar to B. So in general, if B is similar to A, then A is also similar to B. In this case, we say matrices A and B, they are similar matrices. Or we can say A and B, they are similar to each other. Next, let me introduce diagonalizability. Let A be a square matrix. If A is similar to a diagonal matrix D, which means inverse of P times A times P equal to D, for some invertible matrix P, then we say A is diagonalizable. So If A is similar to a diagonal matrix D, then we say A is diagonalizable. Note, in the above situation, we say matrix P diagonalize A. If inverse of P times A times P, if inverse of P times A times P equal to a diagonal matrix, we say matrix P diagonalize A. Next, let's create a theorem. Let A be a n by n square matrix. Then A is diagonalizable if and only if A has n linearly independent eigenvectors. This theorem is in the form of if and only if. In order to prove this theorem, we must prove in both directions. So we first assume A is diagonalizable and prove that A has n linearly independent eigenvectors. Next, we assume A has linearly independent eigenvectors and then prove that A is diagonalizable. So let's prove from left to right first. Assume A is diagonalizable. We try to prove that A has n linearly independent eigenvectors. Since A is diagonalizable, then there exists an invertible matrix P. Such that inverse of P times A times P equal to D, where D is a diagonal matrix. D is a diagonal matrix. Since D is a diagonal matrix, I can let D be the matrix with lambda 1, lambda 2, and lambda n in the main diagonal, then zeros elsewhere, and zeros elsewhere. So D is a diagonal matrix with lambda 1, lambda 2, lambda n in the main diagonal, and zeros elsewhere. Next, let P be the matrix P11, P12, and P1n, P21, P22, P2n, Pn1, Pn2, Pn. With column vectors, P1, P2, Pn. So that's P1, that's P2, that's Pn. Next, since P is invertible, then by the equivalent statements, the column vectors P1, P2, Pn, they are linearly independent. By the equivalent statements. Hence, since they are linearly independent, they cannot be zero vectors. Since P1, P2, Pn they are linearly independent, they cannot be zero vectors. hence P1 is not 0, P2 is not 0, and Pn is not 0. They are not 0 vectors. Since they are linearly independent, they cannot be 0 vectors. Next, since inverse of P times A times P is D, I can multiply both sides by P. Next, since inverse of P times A times P equal to D, then if I multiply both sides by P, I have AP equal to PD. If I multiply both sides by P, I have AP equal to PD. What's AP? What's AP? The left side, AP can be written as A times P, and P has column vectors P1, P2, and Pn. Then if I take A times P, the first column will be AP1, second column will be AP2, and continue, the n column will be APn. That's AP. Now, how about PD? How about PD? If we take P times D, what do we get? If we take P times D, P is the matrix P11, P12, P1n in the first row, P21, P22, P2n in the second row, and Pn1, Pn2, Pnn in the last row. D is a diagonal matrix with lambda 1, lambda 2, lambda n main diagonal, and 0 elsewhere. If we multiply the matrix, what do we get? When we multiply, take row times column. First row times first column is lambda 1, P11. Second row times first column is lambda 1, P21. Nth row times first column is lambda 1, Pn1. Next, take first row times second column, I get lambda 2, P12. Second row times second column, I get lambda 2, P22. Continue. Nth row times second column, I get lambda 2, Pn2. Continue. First row times last column, I get lambda n, P1n. Second row times last column, I get lambda n, P2n. Then last row times last column, I get lambda n, Pnn. This matrix can be written as lambda 1 times column vector P1 in the first column. This is lambda 1 times first column vector P1. Second column is lambda 2 times the second column vector P2. And the nth column is lambda n times the nth column Pn. Lambda n times the nth column vector Pn. Here P1, P2, Pn, they are the column vectors. First column is lambda 1 times first column vector. Second column is lambda 2 times the second column vector. And nth column is lambda n times the nth column vector. Since AP is the same as PD, then the first column must be the same as the first column. Now we have AP1 equal to lambda P1. Then we have AP1 equal to lambda P1 equal to lambda 1 P1. AP2 equal to lambda 2 P2. And continue. APn equal to lambda n Pn. Here, since P1, P2, Pn, they are non-zero vectors. Since P1, P2, Pn, they are non-zero vectors. And matrix A times P1 equal to a scalar multiple of P1. That means P1 is the eigenvector of matrix A. Similarly, P2, P3 until Pn, they are all eigenvectors of matrix A. So P1, P2, Pn, they are all eigenvectors of matrix A. Since P1, P2, Pn, they are linearly independent. So A has n linearly independent eigenvectors. Hence A has n linearly independent eigenvectors. Since P1, P2, Pn, they are all linearly independent. So we complete the proof from left to right. Next, we try to prove from right to left. Assume A has n linearly independent eigenvectors. We try to prove that A is invertible. Next, we assume A has n linearly independent eigenvectors. We try to prove that A is diagonalizable. Let P1, P2, Pn be the linear independent eigenvectors of matrix A. With corresponding eigenvalues, lambda 1, lambda 2, lambda n. With corresponding eigenvalues, lambda 1, lambda 2, lambda n. Then A times P1 equal to lambda 1 times P1. A times P2 equal to lambda 2 times P2. And continue until A times Pn equal to lambda n times Pn. Since P1, P2, Pn, they are eigenvectors, and their corresponding eigenvalues is lambda 1, lambda 2, lambda n. Next, let P be the matrix formed by column vectors P1, P2, Pn. Let P be the matrix formed by these column vectors P1, P2, Pn. We treat P1, P2, Pn as column vectors, and these column vectors form a matrix called matrix P. So let P be this matrix. Then AP, what's AP? AP is A times the matrix P1, P2, Pn. If I multiply AP, I have first column AP1, second column AP2, and the nth column APn. If I multiply AP, that's what I get. I have AP1 in the first column, AP2 in the second column, and APn in the nth column. Next, AP1 is lambda 1 times P1. AP1 equal to lambda 1 times P1. So the first column can be written as lambda 1 times P1. Similarly, AP2 is lambda 2 times P2. Second column can be written as lambda 2 times P2. And continue, the nth column can be written as lambda n times Pn. Now, assume the component of P1 is P11, P21, and Pn1. Assume the component of P2 is P21, P12, P22, and Pn2. Assume the component of Pn. Assume the component of Pn is P1n, P2n, and Pnn. When we multiply, we get a matrix lambda 1 times P11, lambda 1 times P21, and lambda 1 times Pn1 in the first column, lambda 2 times P12, lambda 2 times P22, and similarly lambda 2 times Pn2 in the second column. Continue, we have lambda n times P1n, lambda n times P2n, and lambda n times Pnn in the nth column. That can be written as matrix P11, P12, P1n, P21, P22, P2n, Pn1, Pn2, Pnn times a diagonal matrix lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, 0, lambda n. Let me call this matrix D. This is matrix P. This is matrix P that has P1 in the first column, P2 in the second column, Pn in the nth column. This is matrix P. Let me call this matrix D. Let D be the matrix with lambda 1, lambda 2, lambda n in the main diagonal, and 0 elsewhere. Let D be the diagonal matrix with lambda 1, lambda 2, lambda n in the main diagonal, and 0 elsewhere. Then AP equal to PD. And here, AP equal to P times D. Matrix AP equal to matrix P times matrix D. Next, since matrix P has column vectors P1, P2, Pn, and column vectors P1, P2, Pn, they are linearly independent eigenvectors. Then P must be invertible by equivalent statements. P must be invertible since all column vectors are linearly independent. Since the column vectors are linearly independent, P must be invertible by the equivalent statements. Then matrix P is invertible by the equivalent statements. Since all column vectors of P are linearly independent, P must be invertible by the equivalent statements. So inverse of P is this. Next, if I multiply both sides by inverse of P, I get inverse of P times A times P equal to inverse of P times D. If I multiply both sides by inverse of P, I get this. On the right side here, inverse of P cancels P, we get D by itself. Hence, inverse of P times A times P equal to D. That means A is diagonalizable. If A times inverse of P times P equal to D, that means A is diagonalizable. Hence, matrix A is diagonalizable. Let's complete the proof of this theorem. So, matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. Next theorem, let A be a n by n square matrix. If A has n distinct eigenvalues, then A is diagonalizable. How can we prove this theorem? First of all, since A has n distinct eigenvalues, according to the theorem in the earlier section, we know that if A has n distinct eigenvalues, then A has exactly n linearly independent eigenvectors. So, according to the theorem in the earlier section, we know that A has exactly n linearly independent eigenvectors. Next, find the previous theorem. If A is diagonalizable, if and only if A has n linearly independent eigenvector. So, by the previous theorem, since A has n linearly independent eigenvectors, A is diagonalizable. Let's complete the proof. So, if A has n distinct eigenvalues, then A is diagonalizable. Next, let's do some examples. Diagonalize each of the following matrices if possible. First example, that's a 2 by 2 matrix. How can we diagonalize this matrix? In general, in order to diagonalize a matrix, we need to find eigenvectors first. This is a 2 by 2 matrix. If we can find two linearly independent eigenvectors, then this matrix is diagonalizable. Otherwise, if we cannot find two linearly independent eigenvectors, this matrix is not diagonalizable. So let's find eigenvectors first. In order to find an eigenvector, we must find eigenvalues first. So first of all, compute lambda I minus the matrix A. Lambda I, this is a 2 by 2 matrix. So I's I is 1, 0, 0, 1 minus matrix A. Matrix A is A, negative 10, 3, negative 3. Then distribute lambda. Distribute lambda. We get lambda 0, 0, lambda. Next, distribute negative sign. We get negative A, 10, negative 3, 3. Then add them up. If I add them up, I get lambda minus A, 10, negative 3, and lambda plus 3. Next, find the determinant of this matrix. Let's call a characteristic polynomial. Let's call a characteristic polynomial. Find determinant, cross multiply and subtract. We get lambda minus A times lambda plus 3 minus negative 30. Then simplify. Minus negative 30 is plus 30. Then simplify. We have lambda squared minus 5 lambda minus 24 plus 30. If we factor, we get lambda squared minus 5 lambda plus 6. Then factor, we get lambda minus 2 times lambda minus 3. Set equal 0. Let's call a characteristic equation. This is called a characteristic equation. Solve the equation, we get lambda equal to 2 and lambda equal to 3. Those are the eigenvalues. Those are the eigenvalues. Since this is a 2 by 2 matrix, and we find 2 distinct eigenvalues. According to the previous theorem, this matrix is diagonalizable. Next, let's find eigenvectors. Let's find eigenvectors for each eigenvalue. When lambda is 2, in order to find eigenvectors, we plug 2 into this matrix. We have negative 6, 10, negative 3, and 5. Set equal 0. Set equal 0. Then solve the matrix. Use Gauss-Jordan elimination. I try to make 1 here, leaving 1 here. So I divide first row by negative 6. Divide first row by negative 6. I get 1, negative 3 over 5. Negative 5 over 3. Zero, negative 3, 5, 0. Next, I can multiply first row by 3, add it to the second row. Multiply first row by 3, add it to the second row. I get 1, negative 5 over 3, 0, 0, 0, 0. That's the matrix in the reduced right echelon form. Next, write the first row back to equation. If I want the first row back to equation, I have S1 minus 5 over 3 S2. Equal to 0. Since S1 is a leading variable, S2 is a free variable. Write S1 in terms of S2. I get S1 equal to 5 over 3 S2. Next, put the solution S1, S2 in columns. Put S1, S2 in columns. Since S2 is a free variable, let S2 be T. Then put the solution in columns. S1, S2. Since S1 equal to 5 over 3 times S2, I get 5 over 3 T. So S1 is 5 over 3 T. S2 itself is T. Then I can pull out T. I get -5/3 and 1. That's the basis of the solution space, which is also the basis of the eigenspace. So for lambda equal to 2, the eigenspace is the span of this vector. Five over 3, it's positive 5/3, comma 1. And an eigenvector could be any non-zero vector in the span. Here, make it easier. I chose the first eigenvector to be 3 times 5/3, comma 1. It could be any multiple of this vector. To make it easier, we prefer to use whole numbers. So I multiply this vector by 3. I get 5, comma 3. That's a corresponding eigenvector of its eigenvalue lambda equal to 2. Next, find eigenvector for lambda equal 3. When lambda equals 3, we plug 3 into this equation. We get -5, 10, -3, and 6. Then set equal to 0. Reduce this matrix using the Gauss-Jordan elimination. I can first of all divide first row by -5. I get 1, -2, 0. Leave the second row the same. Next, I can multiply first row by 3, add it to the second row. I get 1, -2, 0, 0, 0, 0. That's in the reduced lower echelon form. Next, write the first row back to equations. I get S1 minus 2S2 equal to 0. S1 is a leading variable. S2 is a free variable. Write the leading variable in terms of a free variable. So I get S1 equal to 2S2. Since S2 is a free variable, let S2 be T. Then put S1, S2 in colors. S1 is 2S2. S2 is T, so I get 2T. S2 by itself is T. Next, I can pull out T. If I pull out T, I get 2, 1. This is the basis of the solution space, which is also the basis of the eigenspace. So the eigenspace corresponding to its eigenvector is spanned by this vector 2, 1. It's the span of this vector 2, 1. Any non-zero vector in the span is eigenvector corresponding to lambda equals 3. Since there's only one vector in the basis, there's only one linear independent eigenvector. That's the second one. We use S2 to represent the second eigenvector. I can use this vector itself, 2, 1. Those are whole numbers. We can use this vector itself, 2, 1. So here we find 2 linear independent eigenvectors. Here we find 2 linear independent eigenvectors. That means this matrix is diagonalizable. Next, how can we diagonalize this matrix? In order to diagonalize this matrix, we try to find an invertible matrix P such that inverse of P times A times T equal to a diagonal matrix D. That's how we diagonalize matrix A. But what's P? What's matrix P? What's matrix P? According to earlier theorem, we know that P is a matrix formed by column vectors P1, P2, Pn. What's P1, P2, Pn here? Here, P1, P2, Pn, they are linear independent eigenvectors of matrix A. So, P can be formed by putting eigenvectors in columns. P can be formed by putting eigenvectors in columns. Here in this problem, we have two eigenvectors, 5, 3 and 2, 1. P can be formed by putting eigenvectors in columns. So I put 5, 3 in the first column and 2, 1 in the second column. That's matrix P. Next, let's find inverse of P. What's the inverse of P? For 2 by 2 matrix, there's a shortcut. It's 1 over the determinant. 1 over determinant. 5 minus 6 times the matrix. For the matrix, interchange the main diagonal. Then change the sign for the other two vectors. Next, multiply. 1 over 5 minus 6. 5 minus 6 is negative 1. 1 over negative 1 is negative 1. So multiply negative 1 to the entire matrix. I get negative 1, 2, that's 3 here. Negative 1, 2, 3, negative 5. This is inverse of P. Next, multiply. D equal to inverse of P times A times P. Inverse of P here is negative 1, 2, 3, negative 5 times matrix A. A is this matrix. A, negative 10, 3, negative 3. P is the matrix 5, 2, 3, 1. Now, if we multiply everything correctly, we should get a diagonal matrix D. If we don't get a diagonal matrix, that means we made a mistake somewhere. Let's multiply the matrix. Row times columns. Row times columns. Negative A plus 6 is negative 2. Row times columns. 10 plus negative 6 is 4. Next, row times columns. 24 plus negative 15 is 9. Next, rows times columns. Negative 30 plus 15 is negative 15. Next, take the product, multiply by the third matrix. 5, 2, 3, 1. Let's multiply. Row times columns. Negative 10 plus 12 is 2. Next, rows times columns. Negative 4 plus 4 is 0. Next, rows times columns. 45 plus negative 45 is 0. Next, rows times columns. 18 plus negative 15 is 3. That's a diagonal matrix. That's a diagonal matrix. That's a diagonal matrix D. That's how we diagonalize this matrix. And in general, if we multiply everything correctly, we should have an eigenvalue in the main diagonals. If we multiply everything correctly, we should have an eigenvalues in the main diagonal. For the first vector 5, 3, its corresponding eigenvalue is 2. We should have 2 in the first row. Second eigenvector is 2, 1. Its corresponding eigenvalue is 3. We should have 3 in the second row. So that's the first eigenvalue. That's the second eigenvalue. If we multiply everything correctly, we should have an eigenvalue in the main diagonals. That's what this theorem says. If we multiply everything correctly, we have eigenvalues lambda 1, lambda 2, lambda n in the main diagonals. And here, lambda 1 is an eigenvalue of the first column vector. Lambda 1 is an eigenvalue of the first column vector. Lambda 2 is an eigenvalue of the second column vector. And lambda n is an eigenvalue of the last eigenvector. So if we multiply correctly, number 2 should be the eigenvalue of this eigenvector, 5, 3. And number 3 should be the eigenvalue of the second vector, 2, 1. That's how we diagonalize this matrix. Next example, this is a 2 by 2 matrix, and we try to diagonalize this matrix. In order to diagonalize this matrix, let's find eigenvalues and eigenvectors first. So in order to find eigenvalue, we first of all compute lambda I minus the matrix A. This is a 2 by 2 matrix. So I is the matrix 1, 0, 0, 1 minus this matrix A, -4, 9, -4. Then distribute lambda, distribute negative sign. We get lambda, 0, 0, lambda. If we distribute negative sign, we get -A, +4, -9, +4. Then adding up, we get lambda minus A, 4, -9, lambda +4. Next, compute the determinant of this matrix. Compute the determinant of lambda I minus A. That's the characteristic polynomial. We get lambda minus A times lambda +4 minus -36. That's the same as +36. Then multiply. We get lambda squared minus 4 lambda plus minus 32. Plus 36. Then combine like terms. We get lambda squared minus 4 lambda plus 4. If we factor, we get lambda minus 2 times lambda minus 2, which is lambda minus 2 squared. Set equal 0. This is called a characteristic equation. Set equal 0. This is called a characteristic equation. Then solve the characteristic equation, we get lambda equal to 2. That's an eigenvalue. That's an eigenvalue. Next, based on eigenvalue, find eigenvectors. When lambda is 2, we plug 2 into this matrix, lambda I minus A. 2 minus A is -6. 4, -9. 2 plus 4 is 6. Next, set equal 0. Then reduce this matrix using the Gauss-Jordan elimination. Solve the system of equations using the Gauss-Jordan elimination. Here I can first of all divide first row by -6. I get 1, -2/3, 0 in the first row. Leave second row the same. Next, I multiply first row by 9, add it to the second row. Multiply first row by 9, add it to the second row. I get 1, -2/3, 0, 0, 0, 0. Next, rerun the first row back to equation. So first row can be written as S1 minus 2/3 of x equal to 0. Here, S1 is a leading variable. S2 is a free variable. Run the leading variable into the free variable. We get S1 equal to 2/3 of S2. Since S2 is a free variable, let S2 be t. Then put the solution S1, S2 in columns. Here, S1 is 2/3 x2. S2 is t. So you get 2/3 t. S2 by itself is t. Next, I can pull out t. If I pull out t, I get 2/3, 1. That's the basis of the solution space, which is also the basis of the eigenspace corresponding to lambda equal to 2. So the eigenspace is spanned by this vector. Since there's only one vector in the basis of an eigenspace, there's only one linear independent eigenvector. Eigenvector could be any multiple of this, could be any non-zero multiple of this vector. In order to make it easier, I multiply this vector by 3 so I can get whole numbers. So for an eigenvector, I use 3 times the basis vector, which is 2, 3. So that's the linearly independent eigenvector corresponding to lambda equal to 2. Since there's only one eigenvalue and there's only one linearly independent eigenvector, for a 2 by 2 matrix, this matrix is not diagonalizable. So this matrix is not diagonalizable. Next example, we have a 3 by 3 matrix. Diagonalize this matrix if possible. In order to diagonalize a matrix, let's find the eigenvalue and eigenvectors first. So let's first of all compute lambda I minus the matrix. Here A is a 3 by 3 matrix. So I should be 1, 0, 0, 0, 1, 0, 0, 0, 1. That's matrix I. A is this matrix. Negative 3, 1, negative 3. 1, negative 3, 3. 1, negative 1, 1. Next, distribute lambda. We get lambda 0, 0, 0, lambda 0, 0, 0, lambda. Distribute negative sign. We get 3, negative 1, 3, negative 1, 3, negative 3, negative 1, 1, negative 1. Then add the matrix up. We get lambda plus 3, negative 1, 3, negative 1, lambda plus 3, negative 3, negative 1, 1, lambda minus 1. Next, find the determinant of this matrix. What determinant of lambda I minus A? That's the characteristic polynomial. What determinant of this matrix? That's called a characteristic polynomial. So for a 3 by 3 matrix, we must use cofactor expansion. Let me take cofactor expansion around the first row. I get lambda plus 3 times the determinant of the submatrix. Lambda plus 3, negative 3, 1, lambda minus 1. Minus negative 1 times determinant of the submatrix. Negative 1, negative 3, negative 1, lambda minus 1. Plus 3 times determinant of the submatrix. Negative 1, lambda plus 3, negative 1, 1. Simplify. We get lambda plus 3 times lambda plus 3 times lambda minus 1 minus negative 3. Minus negative 1 is positive 1. That's negative 1 times lambda minus 1 minus 3 plus 3 times negative 1 minus is plus lambda plus 3. Then simplify. We get lambda plus 3 times lambda squared plus 2 lambda minus 3 plus 3. They can cancel. In the second parenthesis, we get negative lambda plus 1 minus 3, that's minus 2. In the last parenthesis, we get lambda plus 2. Now, in the first term here, I can factor lambda out. If I pull out lambda, I get lambda times x plus 3 times lambda plus 2. In the second parenthesis, I can pull out -1. I get -1 times lambda plus 2. In the third parenthesis, leaving the way it is, 3 times lambda plus 2. Next, I can factor. I can pull out lambda plus 2. If I pull out lambda plus 2, what's left is lambda times lambda plus 3 minus 1 plus 3. Then distribute, we get lambda squared plus 3 lambda plus 2. Factor, we get lambda plus 2 times lambda plus 1. That can be rewritten as lambda plus 2 squared times lambda plus 1. Then set this equal to 0. This is called a characteristic polynomial. This is called the characteristic equation. Set the characteristic polynomial equal to 0. That's called a characteristic equation. Next, solve the characteristic equation. We get two solutions. Lambda equal to -2 and lambda equal to -1. Next, based on the eigenvalues, find the corresponding eigenvectors. When lambda is -2, we plug -2 into the matrix lambda I minus a. Plug -2 here. In the first row, -2 plus 3 is 1. We get 1, -1, 3. In the second row, if I plug in -2 here, -2 plus 3 is 1. So we get -1, 1, -3. In the third row, plug in -2 here. -2 minus 1 is -3. So we get -1, 1, -3. That's the third row. Next, set each row equal to 0. Then solve the system of equations using the Gauss-Jordan elimination. Let's reduce the matrices. I can first of all add row 1 to row 2. If I add row 1 to row 2, first row stays the same. I get 1, -1, 3, 0. If I add row 1 to row 2, the entire row becomes 0. Next, I can add the first row to the third row. When I add the first row to the third row, the entire row becomes 0. I get 0, 0, 0, 0. That's in the reduced row echelon form. Next, rewrite the first row back to equation. First row can be noted as S1 minus S2 plus X3 plus 3x3 equal to 0. Here, S1 is a leading variable. S2, S3, they are free variables. Write the leading variable in terms of free variable. We get S1 equal to S2 minus 3x3. Since S2, S3, they are free variables, let X2 equal to T, X3 equal to S. Then the solution, S1, S2, X3 can be written as S1 equal to S2 minus 3x3, which is T minus 3S. S2 is T, S3 is S. Since there are two variables, write T in a column and write S in a different column. Right, first column is T, T, 0. And the second column is -3, -3S, 0S. Next, in the first column, factor T out. We get 1, 1, 0. In the second column, factor S out. We get -3, 0, 1. Those are the basis, these two vectors are the basis of the solution space, which is the basis of the eigenspace. So the eigenspace corresponding to this lambda is spanned by these two vectors. 1, 1, 0, and -3, 0, 1. Since there are two vectors in the basis of eigenspace, we can find two linearly independent eigenvectors corresponding to this lambda equal to -2. So the linearly independent eigenvectors are S1 equal to 1, 1, 0. S2 equal to -3, 0, 1. Those are the linear independent eigenvector corresponding to lambda equal to -2. Next, find eigenvector where lambda is -1. When lambda is -1, we plug -1 into this matrix, lambda I minus A. Plug -1 here. In the first row, -1 plus 3 is 2. So first row is 2, -1, 3. Next, plug -1 into the second row. -1 plus 3 is 2. So second row is -1, 2, -3. Next, plug -1 into the third row. In the third row, -1 minus 1 is -2. So the third row is -1, 1, -2. Next, set each row equal to 0. Set each row equal to 0. Then solve the system of equations using the Gauss-Jordan elimination. First of all, in the first row, try to make a leading one here. What I can do is I can add a second row to the first row. If I add a second row to the first row, I get 1, 1, 0, 0. Leave the rest the same. Next, there's a leading one here. I try to make everything below leading one to be 0. So I can add row 1 to row 2. If I add row 1 to row 2, I get 1, 1, 0, 0. First row stays the same. Second row is 0, 3, -3, 0. Next, add the first row to the third row. I get 0, 2, -2, 0. Next, in the second row, try to make the first non-zero entry to be a leading one. So I can divide second row by 3. If I divide second row by 3, first row stays the same. Second row becomes 0, 1, -1, 0. Third row stays the same. Next, there's a leading one here. I try to make an entry above and below leading one to be 0. So I can multiply second row by -1, add it to the first row. Multiply second row by -1, add it to the first row. I get 1, 0, 1, 0. Next, I can multiply second row by -2, add it to the third row. First of all, second row stays the same. Multiply second row by -2, add it to the third row. I get 0, 0, 0, 0. That's in the reduced row echelon form. Next, rewrite the first row, second row back to equations. I have S1 plus x3 equal to 0. S2 minus x3 equal to 0. Here, in the first column, second column, they are leading ones. That means S1, S2, they are leading variables. In the third column, there are no leading variables, which means x3 is a free variable. Next, write the leading variable in terms of free variable. We get S1 equal to -x3 and S2 equal to positive x3. Since x3 they are free variables, let x3 be t. Then write the vector S1, S2, x3 in columns. S1 is negative x3, which is negative t. S2 is x3, x3 is t. S3 by itself is also t. Next, I can factor t out. If I factor t out, I get negative 1, 1, 1. That's the basis of the solution space, which is also the basis of the Eigen space corresponding to lambda equal to negative 1. So the Eigen space is spanned by this vector, negative 1, 1, 1. Since there's only one vector in the basis, there's only one linear independent eigenvector. We have x1, x2. Let me call this vector x3. It could be any multiple of this vector. So we can use this vector itself. Negative 1, 1, 1. Those are the independent eigenvectors. Those are the independent eigenvectors. Since this is a 3 by 3 matrix, and we find 3 linear independent eigenvectors, that means this matrix is diagonalizable. Next, let's try to diagonalize this matrix. In order to diagonalize this matrix, we need to find invertible matrix P such that inverse P times A times P equal to a diagonal matrix D. What's P? Here, for matrix P, we put eigenvectors in columns. We put these 3 linear independent eigenvectors in columns. So for first column, I write 1, 1, 0. For the second column, I write negative 3, 0, 1. For the third column, write negative 1, 1, 1. For matrix P, put the 3 linear independent eigenvectors in columns. Next, compute inverse of P. Compute inverse of P. For a 3 by 3 matrix, we must go through the long way to find inverse matrix of P. So first of all, write matrix P. Write matrix P in the form, followed by an identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Then reduce this matrix completely, making the first part of identity. Then the second part will be inverse matrix of P. So let's reduce the matrix. I can first of all multiply first row by negative 1, add it to the second row. First row stays the same. 1, negative 3, negative 1. 1, 0, 0. 0, 3, 2. Negative 1, 1, 0. Leave the third row the same. 0, 1, 1, 0, 0, 1. Next, in the second row, try to make the first non-zero entry to be a 1. I can simply interchange the second row and the third row. So interchange row 2 and row 3. First row stays the same. I get 1, negative 3, negative 1, 1, 0, 0. Interchange row 2 and row 3. I get 0, 1, 1, 0, 0, 1, 0, 3, 2. Negative 1, 1, 0. Now that's the leading one in the second row. We try to make the entries above and below leading one to be 0. So I can multiply second row by 3, add it to the first row. 3 times row 2 plus row 1. I get 1, 0, 2, 1, 0, 3. Leave the second row the same. I get 0, 1, 1, 0, 0, 1. Next, multiply second row by negative 3. Add it to the third row. Multiply second row by negative 3. Add it to the third row. I get 0, 0, -1, -1, 1, -3. Next, in the third row, try to make leading one here. So multiply the third row by -1. We leave the first two rows the same. Then we copy the first two rows over. First row is 1, 0, 2, 1, 0, 3. Second row is 0, 1, 1, 0, 0, 1. Multiply the third row by -1. We get 0, 0, 1. -1, 3. Now, there's a leading one here. Next, try to make all entries above leading one to be 0. I can multiply third row by -2, add it to the first row. Multiply third row by -2, add it to the first row. I get 1, 0, 0. -1, 2, -3. Leave. Multiply third row by -1, add it to the first row. Next, multiply third row by -1, add it to the second row. Multiply third row by -1, add it to the second row. I get 0, 1, 0. -1, +1, -2. Then leave the third row the same. I get 0, 0, 1, 1, -1, 3. This is inverse of P. This matrix is inverse of P. Once we make the first part to be identity matrix, the second part is inverse matrix of P. Next, let's compute diagonal matrix D. D equal to inverse matrix of P times A times P. Inverse of P here is -1, 2, -3, -1, 1, -2, 1, -1, 3. That's inverse of P. Times matrix A. Matrix A is the original matrix. -3, 1, -3, 1, -3, 3, 1, -1, 1. -3, 1, -3, 1, -3, 3, 1, -1, 1. That's matrix. That's an original matrix. Next, times matrix P. This is matrix P. 1, -3, -4 in the first row. One, 0, 1 in the second row. 0, 1, 1 in the third row. Then let's multiply the matrix. Take row times column. 3 plus 2 plus -3 is 2. Next, row times column. -1 plus -6. -1 plus -6 is -7. -7 plus 3 is -4. Next, row times column. That's 3 plus 6, which is 9. 9 plus -3 is 6. Next, second row. Row times column. 3 plus 1 is 4. 4 plus negative 2 is 2. Next, second row times second column. Negative 1 plus negative 3 is negative 4. Negative 4 plus 2 is negative 2. Next, row times column. 3 plus 3 is 6. 6 plus negative 2 is 4. Next, row times column. Negative 3 plus negative 1 is negative 4. Negative 4 plus 3 is negative 1. Next, row times column. 1 plus 3 is 4. 4 plus negative 3 is 1. Next, row times column. Negative 3 plus negative 3 is negative 6. Negative 6 plus 3 is negative 3. That's the third row. So that's the product of these two matrices. Next, times the third matrix. 1, negative 3, negative 1, 1, 0, 1, 0, 1, 1. Then multiply the matrix. Use row times column. Row times column. 2 plus negative 4 is negative 2. Negative 2 plus 0 is negative 2. Next, row times column. Negative 6 plus 0 plus 6 is 0. Next, row times column. Negative 2 plus negative 4 is negative 6. Negative 6 plus 6 is 0. Next, row times column. 2 plus negative 2. 2 plus negative 2 is 0. 0 plus 0 is 0. Next, row times column. Negative 6 plus 0 plus 4. Negative 6 plus 4 is negative 2. Next, row times column. Negative 2 plus negative 2 is negative 4. Negative 4 plus 4 is 0. Next, row times column. Negative 1 plus 1 is 0. 0 plus 0 is 0. Next, row times column. 3 plus 0 is 3. Plus negative 3 is 0. Next, row times column. 1 plus 1 is 2. 2 plus negative 3 is negative 1. So that's a diagonal matrix. If we multiply everything correctly, these three numbers should be eigenvalues. First number should be the eigenvalue of the first vector in P. The second number should be the eigenvalue of the second vector in P. And the third number should be the eigenvalue of the third vector in P. So for the first vector, 1, 1, 0, its eigenvalue is negative 2. For the second vector, negative 3, 0, 1, its eigenvalue is also negative 2. For the third vector, negative 1, 1, 1, its eigenvalue is negative 1. So it should be negative 2, negative 2, negative 1. So we have negative 2, negative 2, negative 1. That's how we diagonalize a 3 by 3 matrix. Next example, diagonalize this 3 by 3 matrix if possible. So, in order to diagonalize a matrix, let's first of all find eigenvalues and eigenvectors first. So let's first of all compute lambda I minus A. Here, since this is a 3 by 3 matrix, I should be a 3 by 3 identity matrix. So I should be 1, 0, 0, 0, 1, 0, 0, 0, 1. Minus A. This is matrix A. 3, negative 3, negative 2. Negative 4, 9, 4. A, negative 15, negative 7. Next, let's simplify. Distribute lambda first. We get lambda 0, 0, 0, lambda 0, 0, 0, lambda. Next, distribute negative 1. We get negative 3, 3, 2, 4, negative 9, negative 4, negative 8, 15, 7. Next, adding up. We get lambda minus 3, 3, 2 in the first row, 4, lambda minus 9, negative 4 in the second row, negative 8, 15, lambda plus 7 in the third row. Next, let's compute the determinant of the matrix lambda I minus A. One determinant of this matrix, that's the characteristic polynomial. Since this is a 3 by 3 matrix, we must use the cofactor expansion. Here, let me use the cofactor expansion on the first row. I get lambda minus 3 times determinant of the submatrix, lambda minus 9, negative 4, 15, lambda plus 7, minus 3 times determinant of the submatrix, 4, negative 4, negative 8, and lambda plus 7, plus 2 times determinant of the submatrix, 4, lambda minus 9, negative 8, and 15. Then simplify. We get lambda minus 3 times lambda minus 9 times lambda plus 7 minus is plus 60 minus 3 times 4 times lambda plus 7 minus 32 plus 2 times 60 minus is plus 8 times lambda minus 9. Next, simplify. Inside the bracket, we get lambda squared minus 2 lambda minus 63 plus 60, that's minus 3. For the second term, inside the bracket, we have 4 lambda minus 28 plus 28 minus 32 is negative 4. In the third bracket, we have 8 lambda minus 72 plus 60, that's minus 12. Then distribute. We get lambda cube minus 2 lambda squared minus 3 lambda minus 3 lambda squared plus 6 lambda plus 9. Distribute 3, we get minus 12 lambda plus 12. Distribute 2, we get plus 16 lambda minus 24. Next, combine like terms. We get lambda cube minus 5 lambda squared, negative 3 lambda plus 6 lambda is 3 lambda. 3 lambda minus 12 lambda is negative 9 lambda. Negative 9 lambda plus 16 lambda is 7 lambda. Then add a constant. 9 plus 12 is 21. 21 minus 24 is negative 3. That's the characteristic polynomial. If I set equal to 0, this is a characteristic equation. Next, solve this equation for lambda. Now, this is a third degree polynomial. There's no shortcut to factor this polynomial. We have to try. If I plug in 1 to this polynomial, what do we get? Let's call this P of x, P of lambda. If I plug in 1, what do we get? If we plug in 1, we get 1 minus 5 plus 7 minus 3, which is 0. If I plug in 1, I get 0. That means x minus 1, lambda minus 1 is a factor of this polynomial. That means lambda minus 1 is a factor of this polynomial. Since lambda minus 1 is a factor, I can take this polynomial, divide by lambda minus 1. So take this polynomial, divided by lambda minus 1. We know that lambda times lambda squared is lambda cube. So put lambda squared here. Multiply lambda squared to lambda minus 1. We get lambda cube minus lambda squared. Then subtract. We get negative 5 lambda squared minus lambda squared is negative 4 lambda squared. Carry the rest. And we know that lambda times negative 4 lambda is 4 lambda squared, negative 4 lambda squared. Then multiply 4 lambda to both of them, to both terms. I get negative 4 lambda squared minus 4 lambda. Then subtract. This is plus 4 lambda. Then subtract. We get 3 lambda minus 3. And we know that lambda times 3 is 3 lambda. Put 3 here. Then multiply 3 to lambda minus 1. We get 3 lambda minus 3. There's no remainder when we subtract. Which means, if I take the polynomial p of lambda, divide by lambda minus 1, I get this quotient. There's no remainder. That means this polynomial can be factored as lambda minus 1 times lambda squared minus 4 lambda plus 3. So, the characteristic polynomial lambda cube minus 5 lambda squared plus 7 lambda minus 3 equals 0. It can be factored as lambda minus 1 times lambda squared minus 4 lambda plus 3. Next, this polynomial is factorable. This is factorable. It can be factored as lambda minus 3 times lambda minus 1. So this characteristic equation can be written as lambda minus 1 squared times lambda minus 3 equal to 0. Solve the equation, lambda equal to 1 and lambda equal to 3. Those are the eigenvalues of the matrix. Those are the eigenvalues of the matrix. Next, find the eigenvectors for each eigenvalue. When lambda equal to 1, we plug in 1 into this matrix, lambda I minus A. Plug in 1 here. In the first row, 1 minus 3 is negative 2. So first row is negative 2, 3, 2. If I plug 1 into the second row, 1 minus 9 is negative A. So second row is 4, negative A, negative 4. If I plug 1 into the third row, 1 plus 7 is A. So the third row is negative A, 15, positive A. Next, set each row equal to 0. Then solve the system of equations using the Gauss-Jordan elimination. First of all, in the first column, try to make leading 1. In a simpler ways, in the second row, I can divide second row by 4 to make 1 here. In the second row, if I divide second row by 4, I can make 1 here. So divide second row by 4. Leave first row the same. Leave the third row the same. Next, I can interchange row 1 and row 2. I get 1, negative 2, negative 1, 0. Negative 2, 3, 2, 0. negative A, 15A, 0. Now that's the leading one here. Try to make all entries below leading one to be 0. So I multiply first row by 2, add it to the second row. I get 1, negative 1, negative 1, negative 2, negative 1, 0. 0, negative 1, 0, 0. Next, I can multiply first row by A, add it to the third row. I get 0, negative 16 plus 15 is negative 1, that's 0, 0. Next, in the second row, try to make the first non-zero entry to be a 1. So I multiply second row by negative 1. Multiply second row by negative 1. I leave the first row the same. I get 0, 1, 0, 0. Leave the third row the same. Since that's a leading one, try to make all entries above and below leading one to be 0. Next, I can multiply second row by 2. Add it to the first row. I get 1, 0, negative 1, 0. Leave second row the same. Next, I can add the second row to the third row. I get 0, 0, 0, 0. That's in the reduced Rorschach form. Next, write the first row and second row back to equation. So first row can be written as S1 minus S3 equal to 0. Second row can be written as S2 equal to 0. Here, in the first column, second column, they are leading ones. That means S1, S2, they are leading variables. In the third column, there are no leading ones. That means S3 is a free variable. Next, write leading variables in terms of free variable. We get S1 equal to S3. Second equation is S2 equal to 0. Since X3 is a free variable, let X3 be T. Then the vector S1, S2, X3 can be written as S1 is X3, which is T. S2 is 0. X3 is also T. Next, we can factor T out. If I factor T out, I get 1, 0, 1. That's the basis of the solution space, which is also the basis of the eigenspace corresponding to lambda equal to 1. So the eigenspace is spanned by this vector 1, 0, 1. Since there's only one vector in the basis, that means there's only one linearly independent eigenvector in eigenspace. An eigenspace, an eigenvector could be any multiple of this basis vector. So I can use this vector itself, 1, 0, 1. So that's the eigenvector corresponding to lambda equal to 1. Next, let's find an eigenvector when lambda equal to 3. When lambda equal to 3, we plug 3 into the matrix, lambda I minus A. So plug in 3 here. If I plug in 3 here, in the first row, I get 0, 3, 2. In the second row, I get 4 here. 3 minus 9 is negative 6. Negative 4. Negative A, 15. 3 plus 7 is 10. Then set each row equal to 0. Set each row equal to 0. Then solve the system using Gauss-Jordan elimination. First of all, in the first row, try to make a leading one here. Now, it's impossible to make 0 to be a 1. So we can try is, I can divide second row by 4. the only possibility is that divide second row by 4. Divide second row by 4. I get 0, 3, 2, 1, negative 3 over 2. Negative 1. Leave the third row the same. Negative A, 15, 10, 0. Next, we can interchange row 1 and row 2. We get 1, negative 3 over 2, negative 1, 0. 0, 3, 2, 0. Negative A, 15, 10, 0. Next, try to make negative A to be 0. So I multiply first row by A, add it to the third row. So first row stays the same, 1, negative 3 over 2, negative 1, 0. Second row stays the same, 0, 3, 2, 0. Multiply first row by A, add it to the third row. I get 0, A times negative 3 over 2 is negative 12. Negative 12 plus 15 is 3. Negative A plus 10 is 2, 0. Next, in the second row, try to make the first non-zero entry to be a 1. So I can divide second row by 3. I get 1, negative 3 over 2, negative 1, 0. 0, 1, 2 thirds, 0. 0, 3, 2, 0. That's a leading one here. Try to make the entries above and below leading one to be 0. So I can first of all multiply second row by 3 over 2. Add it to the first row. Multiply second row by 3 over 2. Add it to the first row. I get 1, 0. 2 thirds times 3 over 2 is 1. 1 plus negative 1 is 0. 0. Leave second row the same. I get 0, 1, 2 thirds, 0. Next, I can multiply second row by negative 3. Add it to the third row. I get 0, 0, 0, 0. Here. That's in the reduced Rorschach form. Next, rewrite each row. Rewrite the first row and second row back to equation. From first row, I get S1 equal to 0. From second row, I get S2 plus 2 thirds of X3 equal to 0. Here, in the first column, second column, they are leading ones, which means S1, S2, they are leading variables. In the third column, there are no leading ones. That means X3 is a free variable. Next, write the leading variable in terms of free variables. I get S1 equal to 0, S2 equal to negative 2 over 3, S3. Since X3 is a free variable, next, let X3 be T. Then, write S1, S2, X3 in columns. Write S1, S2, X3 in column. S1 is 0. S2 is negative 2 over 3, X3. X3 is T, so I get negative 2 over 3, T. The third row, X3 is T. Next, I can factor T out. If I factor T out, I get 0, negative 2 over 3, and 1. This is the basis of the solution space, which is also the basis of the eigenspace corresponding to lambda equals 3. So the eigenspace is spanned by this vector. Since there's only one vector in the basis of the eigenspace, we can only find one linear independent eigenvector. An eigenvector is the second one. Eigenvector could be any non-zero multiple of the basis vector. So in order to make whole numbers, I multiply this vector by 3. For an eigenvector, I prefer to use whole numbers. So I multiply this vector by 3. I get 3 times negative 2 over 3, comma 1. If I multiply, I get 0, negative 2, 1. So that's an eigenvector corresponding to x equal to 3, corresponding to lambda equal to 3. Now, for this matrix, we only find two linear independent eigenvectors. But this is a 3 by 3 matrix. Which means this matrix is not diagonalizable. Since we only find two linear independent eigenvectors, this 3 by 3 matrix is not diagonalizable. So this is not diagonalizable. Next, let me show you a different problem. Let A be the matrix A, negative 10, 3, negative 3. This is a 2 by 2 matrix. Then, how can we find, for example, how can we find A to the power of 100? Here, since A is a matrix, we try to find A to the power of 100. We use matrix A times matrix A times matrix A, and so on. There's a total of 100 matrices multiplied together. And we know that each matrix A is this 2 by 2 matrix. A, negative 10, 3, negative 3. There's a total of 100 matrices multiplied together. When we multiply these 100 matrices, we multiply the first two matrices first. Take row times column, row times column, row times column, row times column. When we get a product, multiply to the third matrix, and so on. So here you can see that when we try to find A to the power of 100 manually in this way, it's almost impossible. It's almost impossible. If we try to find A to the power of 100 manually in this way, it's almost impossible. However, if matrix A is diagonalizable, then there's a simpler way to find A raised to a higher power manually. Next, let me show you how to find powers of diagonalizable matrices. Let A be a diagonalizable matrix. Then, let I is an invertible matrix P. Such that inverse of P times A times P equal to D, where D is a diagonal matrix. Next, since inverse of P times A times P is D, if I multiply both sides by P, I get P times inverse of P times AP equal to PD. Then on the left side here, P cancels the inverse of P. We get AP equal to PD. Next, if I multiply both sides by inverse of P, I get AP times inverse of P equal to P equal to PD times inverse of P. If I multiply both sides by inverse of P, I get this. Then here, on the left side, P cancels the inverse of P. We get matrix A equal to PD times inverse of P. Now, based on this expression here, A equal to PD times inverse of P. How can I compute A squared? A squared means PD times inverse of P times P times PD times inverse of P. Then in the middle you can see that inverse of P times P is identity matrix, they can cancel. What's left is P times D times D times inverse of P, which is PD squared times P inverse of P. So A squared equal to PD squared times inverse of P. Now, how about A cube? A cube is PD times inverse of P, PD times inverse of P, then another PD times inverse of P. You can see that here in the middle, inverse of P cancels P, inverse of P cancels P. What's left is P in the front, D, D, D in the middle, and inverse of P in the end. Because in the middle, inverse of P times P is identity matrix, they can cancel. Inverse of P times P is identity matrix, they can cancel. What's left is D, D, D in the middle. It's P times D cube times inverse of P. That's A cube. Similarly, how about A to the power of K? For A to the power of K, we have PD times inverse of P, PD times inverse of P, another PD times inverse of P. Continue with PD times inverse of P and the n, PD times inverse of P and the n. There are totally k such vectors. If I cancel inverse of P and P in the middle, if I cancel P and inverse P in the middle, there are totally k d's in the middle. If I cancel inverse of P with P, there are totally k d's left in the middle, since there are k factors here. Since there are k factors, if I cancel inverse of P with P in the middle, what's left is D times D times D times D times D in the middle, and there are k such D's. So you get P times D times D times D times inverse of P and the n. In the middle, there are k D's in the middle. There are k D's in the middle. That's P times D to the power k times inverse of P. So, in general, if matrix A is diagonalizable, and inverse of P times A times P equal to D for some diagonal matrix D, then A to the power k can be written as P times D to the power k times inverse of P. For all positive integer k, this formula works for all positive integer k. Here we can see that using this formula, we can easily raise a to the power of k. Because D is a diagonal matrix, raising a power to a diagonal matrix is very easy. For example, if D is a matrix 1, 2, 3 in the main diagonal, for example, zeros elsewhere, when we compute D to the power of k, we can easily raise the power for every entry in the main diagonal. And 0 stays the same. So for a diagonal matrix, it's very easy to raise it to a higher power. Using this formula, we can easily raise a to any powers. Indeed, if an above matrix A is invertible, then the above formula a to the power k equal to p times d to the power k times the inverse of p. This formula is also true for all negative integer k. If matrix A is invertible, the above formula is also true for all negative integer k. Why is that? If A is invertible, then we know that inverse of A exists. What's inverse of A? Since A equal to P times D times inverse of P, inverse of A is the inverse of this matrix. P times D times inverse of P, inverse. How can we compute the inverse of this product here? When we compute the inverse of product, we write the last matrix first. That's inverse of P inverse times D inverse times P inverse. When we distribute inverse, write the matrices backward. Inverse of P inverse times D inverse times P inverse. And inverse of P inverse is P. The inverse of P inverse is P times inverse of D times inverse of P. And that's inverse of A. How about A raised to negative 2? We know that A raised to negative 2 can be written as inverse of A squared. A raised to negative 2 is inverse of A squared. This is inverse A. So we have P times inverse of D times inverse of P times P times inverse of D times inverse of P. And then in the middle you can see that inverse of P times P is an identity matrix. They can cancel. What's left is P times inverse of D times inverse of D in the middle, and then times inverse of P. In the middle, inverse of P and P, they can cancel. What's left is inverse of D times inverse of D in the middle. And we know that inverse of D times inverse of D is D raised to negative 2. So we get P times D raised to negative 2 times inverse of P. So that's A raised to negative 2. I get this. How about A raised to negative 3? A raised to negative 3 is inverse of A cubed, which means inverse of A times another inverse of A. So that's equal to P times inverse of D times inverse of P. P times inverse of D times inverse of P times another P times inverse of D times inverse of P. In the middle, inverse of P times P can cancel. inverse of P times P is identity matrix, they can cancel. What's left is P times inverse of D times inverse of D times another inverse of D, and then times inverse of P. And we know that in the middle, inverse of D times inverse of D times inverse of D is D raised to negative 3. And in general, we can see that we'll have A to the power of negative L. That can be written as A to the that can be written as inverse of A to the power of L. Next, inverse of A times inverse of A times inverse of A L times. So we get P times inverse of D times inverse of P. P times inverse of D times inverse of P. P times inverse of D times inverse of P. There are L such vectors. Then in the middle, you can see that inverse of P times P is identity matrix, they can cancel. Inverse of P times P is identity matrix, they can cancel. Inverse P times negative P times the next P, they can cancel. And this P will be cancelled by the previous P. What's left is inverse of D times inverse of D times inverse of D in the middle. And there are L such D's. So we get P times inverse of D times inverse of D times inverse of D, then times inverse of P. There are L such D's. There's L such matrices. We have L inverse of D's here. So together, that's P times D raised to negative L. This is the L such inverse of D's times inverse of P. So A raised to negative L equal to P times D to the power of negative L times inverse of P. So this formula is also true for all negative integer k. This is a negative integer. This formula is also true for all negative integer k. Keep it in mind. If matrix A is invertible, this formula is also true for all negative integer k. Next, let's create an example. In the previous example 1, matrix A is diagonalizable and invertible. Compute A to the power of 100 and A to the power of negative 100. We know that in the previous example 1, that's matrix A. A, negative 10, 3, negative 3. This matrix is diagonalizable. And also, since all its eigenvalues are non-zeros, then by the equivalent statements, matrix A is invertible. So this matrix A is diagonalizable and invertible. So we can compute A to the power of 100 and A to the power of negative 100. According to the previous example, we can see that here. Matrix P is 5, 3, 2, 1. This matrix diagonalizes A. Inverse of P is negative 1, 2, 3, negative 5. And the diagonal matrix D is 2, 0, 0, 3. We know that the diagonal matrix D is inverse of P times A times P. Which means matrix A can be written as P times D times inverse of P. So, in order to compute A to the power of 100, according to the previous formula, A to the power of K is P times D to the power of K times inverse of P. So, A to the power of 100 can be written as P times D to the power of 100 times inverse of P. Then let's multiply. P is the matrix 5, 3, 2, 1. D is the diagonal matrix 2003. And we raise d to the power of 100. Inverse p is a matrix, -1, 2, 3, -5. Let's do the exponent first. Since d is a diagonal matrix, when we raise the diagonal matrix to the power of 100, we have 2 to the power of 100, 0, 0, 3 to the power of 100. That's a diagonal matrix. When we raise the diagonal matrix to the power of 100, we raise all entries in the diagonal to the power of 100. Zeros stays the same. That's one advantage of using diagonal matrix. Next, let's multiply the matrices. In order to make the computation a little easier, let me make A equal to 2 to the power of 100, B equal to 3 to the power of 100. We can make the computation a little easier. 5, 2, 3, 1 times the diagonal matrix A, 0, 0, B. Then let's multiply the matrices. When we multiply matrices, we use row times columns. Row times column, we get 5A. Row times columns, I get 2B. Row times column, I get 3A. The next row times column, I get 1B. Then multiply by the third matrix, -1, 2, 3, -5. When we multiply matrix, use row times column. I get -5A plus 6B, 10A minus 10B, row times column, -3A plus 3B, row times column, 6A minus 5B. Then for the final answer, replace A and B with these two numbers. For the final answer, replace A and B with these two numbers. We get -5 times 2 to the power of 100 plus 6 times 3 to the power of 100. 10 times 2 to the power of 100 minus 10 times 3 to the power of 100. On the bottom, we have -3 times 2 to the power of 100 plus 3 times 3 to the power of 100. 6 times 2 to the power of 100 minus 5 times 3 to the power of 100. That's how we compute A to the power of 100. Now, how about A to the power of -100? For A to the power of -100, since matrix A is diagonalizable and invertible, this formula is also true. This formula is also true for all negative integer k. So we can use the same formula. A raised to -100 is P times D raised to -100 times inverse of P. And we know that P is a matrix 5, 5, 2, 3, 1. D is a diagonal matrix 2, 0, 0, 3 raised to -100. Inverse P is this matrix -1, 2, 3, -5. Then let's multiply the matrix. Let's compute D raised to -100 first. Since this is a diagonal matrix, when we have diagonal matrix raised to -100, we can simply raise all entries in the main diagonal to the power of -100. I get 2 raised to -100, 0, 0, 3 raised to -100, times inverse of P. That's -1, 2, 3, -5. Next, in order to make the computation a little easier, I replace 2 raised to 100 with letter A. And I replace 3 raised to negative 100 with letter B. I have 5, 2, 3, 1 times the matrix A0, 0, B times negative 1, 2, 3, negative 5. Now here you can see that this matrix, these 3 matrices, and these 3 matrices, they are exactly the same. So their product must be the same. Their product must be the same. It must be negative 5A plus 6B, 10A minus 10B, negative 3A plus 3B, and 6A minus 5B. This matrix, they are exactly the same. Their product must be the same. Next, I can replace A and B with these 2 numbers. So I get negative 5 times A. A is 2 raised to negative 100 plus 6 times B. B is 3 raised to negative 100. 10 times A. A is 2 raised to negative 100 minus 10 times B. B is 3 raised to negative 100. And we have negative 3 times A. A is 2 raised to negative 100 plus 3 times B. B is 3 raised to negative 100. 6 times A. A is 2 raised to negative 100 minus 5 times B. B is 3 raised to negative 100. That's how we compute A raised to negative 100. Next example. In the previous example 3, matrix A is diagonalizable and invertible. Compute A to the power of 200 and A to the power of negative 500. In the previous example 3, you can see that A is this matrix, negative 3, 1, negative 3, 1, negative 3, 3, 1, negative 1, 1. This matrix is diagonalizable. This matrix is diagonalizable. Since all its eigenvalues are non-zeros, this matrix is also invertible by the equivalence statements. Since all its eigenvalues are non-zeros, this matrix is also invertible by the equivalence statements. Since matrix A is diagonalizable and invertible, let's try to compute A to the power of 200 and A to the power of negative 500. In the previous example, we know that matrix P is in this matrix 1, negative 3, negative 1, 1, 0, 1, 0, 1, 1. This matrix diagonalizes A, and its inverse is this matrix. Its inverse is this matrix. Negative 1, 2, negative 3, negative 1, 1, negative 2, 1, negative 1, 3. And the diagonal matrix D is this matrix. That's the diagonal matrix D. D is the matrix negative 2, 0, 0, 0, negative 2, 0, 0, 0, negative 1. That's the diagonal matrix D. And we know that the diagonal matrix D equal to inverse of P times A times P, which means matrix A equal to P times D times inverse of D. We try to compute A raised to 200 and A raised to negative 500. According to the previous formula, we know that A to the power of K is P times D to the power of K times inverse of P. So A to the power of 200, that's P times D to the power of 200 times inverse of P. And here, P is this matrix. 1, negative 3, negative 1, 1, 0, 1, 0, 1, 1. D is its diagonal matrix. -2, 0, 0, 0, -2, 0, 0, 0, -1 to the power of 200. And inverse P is this matrix. -1, 2, -3, -1, 1, -2, 1, -1, 3. Let's multiply the matrices. Let's multiply the diagonal matrix first. So matrix P stays the same. 1, -3, -1, 1, 0, 1, 0, 1, 1. When we raise the diagonal matrix to the power of 200, we raise all entries in the main diagonal to the power of 200. We get -2 to the power of 200, 0, 0, 0, -2 to the power of 200, 0, 0, 0, and -1 to the power of 200. So that's one advantage of using diagonal matrix. It's very easy to raise to a higher power. And inverse of P is -1, 2, -3, -1, 1, -2, 1, -1, 3. Next, let's multiply the matrices. In order to make the computation a little easier, let me let A equal to 2, -2 to the power of 200. And this is also the same as A. This is A, this is also A. They are exactly the same. Let me call this B. In general, we use A, B, C to represent these three numbers. But since the first number and the second number they are exactly the same, I use A to represent both numbers. Let me call this number B. Let B be the number -1 to the power of 200. So this matrix can be written as 1, -3, -1, 1, 0, 1, 0, 1, 1 times the diagonal matrix A, 0, 0, 0. This is also A. They are exactly the same. So I can use A to represent both numbers. 0, 0, B. Multiplied by -1, 2, -3, -1, 1, -2, 1, -1, 3. Let's multiply the first two matrices first. Take row times column. I get A, row times column. I get -3A. Row times column. I get -B. Next, row times column. I get A. Row times column. I get 0. Row times column. I get B. Next, row times column. I get 0. Row times column, I get A. Row times column, I get B. Then multiply by the third matrix. -1, 2, -3, -1, 1, -2, 1, -1, 3. If we multiply, what do we get here? Do the same thing. Use row times column. Row times column. I get -A plus 3A. That's 2A minus B. That's the first entries. Next, row times column. I get 2A minus 3A, which is -A, plus B. Next, row times columns. I get -3A plus 6A, which is 3A, minus 3B. I get 3A minus 3B. Next, with row times column, I get -A plus B. Row times column, I get 2A minus B. Next, row times column, I get -3A plus 3B. Next, row times column, I get -A plus B. Row times column, I get A minus B. Next, row times column. I get negative 2a plus 3b. Then, for the final answer, replace a and b with these two numbers. And here, b is negative 1 raised to 200, which is 1. Negative 1 raised to the power of 200 is 1. Then plug in a and b. So the final answer is 2 times negative 2 to the power of 200. Minus b. B is 1. Negative a, that's negative 2 to the power of 200 plus b. B is 1. 3a, that's negative 2 to the power of 200 minus 3b. B is 1. Negative a plus b, that's negative 2 to the power of 200 plus 1. 2a minus b, that's 2 times negative 2 to the power of 200 minus 1. Negative 3a plus 3b, that's negative 3 times negative 2 to the power of 200 plus 3b, which is 3. Negative a plus b, that's negative 2 to the power of 200 plus 1. A minus b, that's negative 2 to the power of 200 minus 1. Negative 2a plus 3b, that's negative 2 times negative 2 to the power of 200 plus 3. That's how you compute a to the power of 200. Next, how about a to the power of negative 500? Since matrix A is diagonalizable and invertible, this formula is also true for negative integer k. This formula is also true for all negative integer k. So we can use the same formula. For a raised to negative 500, we can use the same formula. That's p times d raised to negative 500 times inverse of p. And we know that p is the matrix. P is the matrix 1, negative 3, negative 1, 1, 0, 1, and 0, 1, 1. D is the diagonal matrix negative 2, negative 2, negative 1. To the power of negative 500. Inverse P is this matrix. So we get negative 1, 2, negative 3, negative 1, 1, negative 2, 1, negative 1, 3. Next, let's multiply. Let's multiply the diagonal matrix first. I get 1, negative 3, negative 1, 1, 0, 1, 0, 1, 1. For the diagonal matrix, if I raise to the power of negative 500, I raise all entries in the main diagonal to the power of negative 500. Raise all entries in the main diagonal to the power of negative 500. I get negative 2 to the power of negative 500, and another negative 2 to the power of negative 500, 0, 0, and negative 1 to the power of negative 500. That's one advantage of using diagonal matrix. We can raise it to higher power very, very easily. It doesn't matter if the power is positive or negative. We can raise it to any power very, very easily. Inverse of P is this matrix stays the same. Next, let's multiply the matrices. In order to make the computation a little easier, let me replace this number with a. So let a be negative 2 to the power of negative 500. This number and this number are exactly the same, so I can use a to represent both numbers. Let b be these numbers, negative 1 to the power of negative 500. then multiply the matrices. This matrix can be written as 1, -3, -1, 1, 0, 1, 0, 1, 1 times the diagonal matrix A 0, 0, 0, A 0, 0, 0, B times this matrix -1, 2, -3, -1, 1, -2, 1, -1, 3. Now here, since this matrix and this matrix, they look exactly the same. This matrix here and this 3 matrix here, they look exactly the same. So their product must be exactly the same. So their product must be this 2a minus b, -a plus b, 3a minus 3b, -a plus b, 2a minus b, -3a plus 3b, -a plus b, a minus b, -2a plus 3b. Then for the final answer, replace a and b with these two numbers. A is -2 to the power of -500, b is -1 to the power of -500. And we know that -1 raised to any even power is 1, is positive 1. -1 raised to any even power is positive 1. Next, let's plug in. So for the final answer, replace a with -2 to the power of -500, replace b with positive 1. I get 2 times -2 to the power of -500 plus 1 minus 1. -2 to the power of -500 plus 1. 3 times -2 to the power of -500 minus 3. And then -2 to the power of -500 plus 1. 2 times -2 to the power of -500 minus 1. -3 times -2 to the power of -500 plus 3. -2 to the power of -500 plus 1. -2 to the power of -500 minus 1. -2 times -2 to the power of -500 plus 3. That's a to the power of -500. That's this matrix, a to the power of -500. So using this formula, we can compute a raised to higher power very, very easily. As long as a is diagonalizable, we can compute a raised to higher power very, very easily.